Now let's go to the topic of today. So I want to talk about control barrier functions. I want to convince you that this is a cool tool that can be used in many different ways. And I want to start by talking about Lyapunov functions. So very basic and standard nonlinear control tool. That I would say it's considered maybe the backbone of any nonlinear control course at the university level and so on. Why do I start with Lyapunov function and what it has to do with control barrier function? That's part of what I want to convey. I want to convince you that these two topics are in some way dual one to each other. They are related in a very elegant way, in my opinion, but also non-trivial. And what I want to do for you is make it trivial today. I want you to understand very easily why Lyapunov functions and control barrier function are, at the end of the day, the same thing and can be treated with the same tools. Okay, so I know that not all of you have background in control. So for who has a background in control, this will be very trivial recap, but I'm trying to be very foundational. I want everyone to keep track of what I'm saying. So in the moment in which we have a dynamical system now, which I represent like x dot equal f of x, is someone not familiar with this notation x dot equal f of x? Or maybe you have an idea of what it means, no? So we represent dynamical systems, roughly speaking, in this way, no? X dot equal f of x, where x is the state of our system. In the moment in which the system is complicated, is nonlinear, as for example, is correspond to the dynamics of a robot or a drone or a fluid or an elastic body or what else, it's very difficult, no, to understand the evolution of the system, to analyze its stability property, the equilibria, and so on, simply because we cannot solve such a system. No? So Lyapunov function is a tool which basically helps to understand something of the system without solving this differential equation, without actually having to solve it. So basically, the existence of a Lyapunov function, which is this positive definite function, okay, this v of x, which is defined on the state space of the system, helps to understand whether some of the equilibria of the system are system in which if you start the system in that point, precisely that point, the system doesn't move, remains there. That's an equilibrium. And these tools of Lyapunov function helps to understand the stability of this equilibrium. Now we know for sure that if we design a Lyapunov function like this one, which I represent with this paraboloid, centered at the equilibrium without loss of generality, I call zero. No, say the equilibrium is zero, and that's this property. Basically, the minimum is in the equilibria, and in some way, along the solutions of the system, we cannot solve the system, but we have a way to understand that the evolution of the system is such that, okay, is such that the v dot, that is the variation along the solution of the system of this Lyapunov, the projection of the state of the system along the Lyapunov function decreases in that space, then the system, the equilibrium is stable. The Lyapunov theory relate the existence of such function to the fact that these equilibria are stable. Okay, this is Lyapunov theory, no? And this is a very basic tool in control theory that everyone knows. I want to everyone who has studied control knows. I want to stress the fact, which is very important in the discussion later, that this is a very specific construction which induces a property, which is the property that the level sets, okay, of such a defined Lyapunov function. The level sets are the sets, okay, in the state space, such that the image of the Lyapunov function assumes value less than a constant c. Okay, like omega c are all the level sets such that the value of the Lyapunov function is less than c. And for such defined Lyapunov function, it means basically If this is the paraboloid, it means the circles, no? For increasing C's, that goes on. And not only this existence of this Lyapunov function implies the fact that this equilibrium is stable, okay? But a little bit more, it happens that locally, these level sets are invariant. Okay, this is an important point. The proof of the fact that the Lyapunov function implies stability of equilibrium uses this fact. What does it mean invariant? Invariance is a very important, very crucial concept in system theory, which says that a set is invariant if in whatever situation I start the system in any point of the set, forever in the future, I am sure that the system will not leave that set. Okay, so of course, one equilibrium is an invariant by definition, because otherwise it wouldn't be an equilibrium. No? The equilibrium is such that I start my system there, I stay there. But in the same way, I can have invariant sets. And this will be crucial in the understanding of control barrier functions. Is this clear? Okay, now a conceptual step further. This is, you see that there is no control here. This is just system dynamics. Now we go from Lyapunov function to control Lyapunov function. What's the difference? Let's consider a control system, which is basically another dynamical system in which we're supposed to have some input. Of course, I'm very non-technical. I'm not talking about smoothness, existence of solution, and blah, 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 but I mean, it cannot, I mean, the price to pay to convey the information in 20, 30 minutes is, I have to be non-technical. But say we have an input of the system, we can control something, so we have a degree of freedom on the dynamics of the system, and let's suppose that the system is affine in the input. What does it mean? That the input enters linearly, some kind of input matrix G of X. Okay, some kind of input vector field. So again, now suppose the task is that by means of control, we want to stabilize a system. We want to stabilize an equilibrium or a set, and so on. Of course, we can think about it the same way as before. Okay, what we can call a control Lyapunov function, a function such that the definition is the same as before. You see, that before we had no control, it was just v dot less than 0. No, now, okay, we want to design a controller, so we can design a controller such that if it exists a controller, a u, such that v dot is less than 0, and we found such a v, then we have reached our goal. Now, in the moment in which we design a controller u, which depends on the state, the system becomes autonomous and again becomes of that type. No, but this formulation is important. No, so it's about the existence of a controller. It's important because in this setting we will span and we will optimize over all the possible controllers, and you have to reason this way if you want to understand the way control barrier functions are used. So basically, a control barrier function is a control Lyapunov function is a Lyapunov function in which we can sweep. We have the degree of freedom of the controller, no? And if we find such a control Lyapunov function, then we stabilize the system, because by definition, the control Lyapunov function is a function such that there exists, I can find a controller such that v dot is less than 0. Okay. And again, as before, once we found the control Lyapunov function, we have invariance of the level sets, because that is then just the Lyapunov function of the control system, exactly as before. So this was a very, very brief and non-technical recap of Lyapunov theory. Okay, what has this to do with barrier function? Clear questions? Okay.
U is a function of X.
Yes, yes, exactly. Say normally, at least I was used to think about when I think about say Lyapunov induced controllers. Now that you you find the Lyapunov function. No? The difficulty is finding one. No? If there exists, then I'm stable. Okay, but then you have to find it. No? And then, for example, people saying PD plus gravity compensation, you can use the quadratic control on the potential is a spring, and then you take the gradient and you have a controller and so on. True. Here we are a bit a step ahead. We are in an optimization framework, no, in the sense that this U, technically speaking, it suffices that it's Lipschitz continuous, no, because you need the U to be a Lipschitz continuous signal to have existence of solution of the closed loop system.
I think the point of is the U function of X is not a constant. The way
It's not a constant, it's not a exogenous.
No, can also be a constant.
could be a constant, but
Yeah,
in general,
In general, is a state feedback. In general, is a state feedback. But my point is that it doesn't require to be a state feedback in closed form or in a smooth. It can be a very funny state feedback. No, it can be a state feedback which is defined pointwise. So for this X, I have this U. For this X, I have this U. For this X, it can be decided by an optimization. But yes, in general, it's a state feedback. Let's put it like that.
Computed based on the current.
It's computed based on the current X. Exactly. Okay, these were Lyapunov function. Let's go to barrier function, and you will initially say, but this is completely unrelated. What has that to do with it? And we will come to it. So barrier functions are similar in the sense that they are a tool to analyze what happens to a system which we cannot calculate the solution of. Okay, see it that it's a help, it's a friend that we have that stores some information about the system. The Lyapunov function store information about stability. No, is an equilibrium stable or not? Is a set invariant? Is a set stable or not? Barrier function does the same for the concept of invariance. Okay, so barrier functions encode in the same way as existence of Lyapunov function implies stability, a system of barrier functions imply invariance. In which way? So barrier functions are defined, and I'm talking about zeroing barrier functions. There are different types of barrier function. We can go to that later, but I'm trying to be conceptually clean. No, let's have a system x dot equal f of x. And let's build a barrier function h of x, which I represent this way, like a paraboloid, but the other way around with respect to a Lyapunov function, in which this barrier function is built in such a way that I encode the set C, okay, as the super level set of this function. That is basically the C is defined as all the x's such that h of x is greater than 0. Okay, 0. It is basically if I have such a defined paraboloid the other way, then if I look it from above, this circle here is the safe set which I build by means of this CBF, of this BF, this barrier function, and the boundary of the safe set is the pre-image under the barrier function of the value 0. Okay, this is how I built it. This is how I built it. And then the existence of an H, of a barrier function H, implies the invariance of the set. What's this H? What's the, in the same way as the Lyapunov function had to be such that V dot is less than 0 to be stable, what does this barrier function has to have in order that the set is really invariant? It has to happen that H dot is greater than 0 for each x at the boundary of the safe set. Okay, you can stare it for 10 seconds and it will be crystal clear. One, no? Say you start the system, the x0, you start the system somewhere here, no? Somewhere inside the safe set. The H is greater than 0 by construction. No? And here you see the condition is only for things happening at the boundary. It's not a continuous condition. No? So inside the system, inside the safe set, the system can do what it wants. I mean, so we have to check invariance of this safe set. We don't care about what happens here. No, we just want that the system does not leave the set. We want to check. It's not because we have no control. There's just analysis, no? And so if the system is such that in the moment in which we touch the boundary of the safe set, the h dot is greater than 0. And the way that the function is built, that means that for some reason, the state goes back to the interior of the safe set. That cannot be otherwise. Now, of course, there are some other technical assumptions for the CBF, like the gradient of the H must be non-vanishing at the boundary. Of course, otherwise you could go, but I mean, I don't want to be technical, no? This is the idea. So if such an H exists, then then C is invariant, yes?
So if you hit the boundaries, you have to return back to the interior.
Yes, yeah.
You don't stay at the boundary.
It's greater than 0. Greater. Yes, yes, exactly. It's greater than 0. And this is Nagumo's invariant principle, 1941. We are in middle World War II. This Japanese guy stated this condition about invariance of the sets. Pretty obvious, no? But 1941. Okay. Okay, let's go from barrier function to control barrier function now. Same story as from Lyapunov function to control Lyapunov function. This is what happens to control barrier function. Say now we have a control system as before. Now the system of the CBF, the control barrier function, is such that there exists a controller, state feedback, such that as before, now the h dot is greater to 0 at the boundary. So that's the difference between invariance and what in control theory is called control invariance. That is, we make a set invariance by means of control. For Lyapunov was the difference between stability and stabilizability. It's what it is. No, one is the autonomous case, and the other is the case that we force it by means of control. Okay. Here we go. I gave a brief explanation of Lyapunov theory, a brief explanation of barrier function theory, how they are connected. Why did I claim that they are dual one to each other? It's not clear, no? And it's very different, no? Here in Lyapunov theory, we had v dot less than 0 for every x but the origin, no? And this funny thing made every level set invariant, so was very restricted in some way, no? Because you cannot go back, no? Once you go towards the 0, you cannot go back with the Lyapunov theory. And instead, here is very different. Here we have h dot greater than 0. Before it was less. Here is greater, but only at the boundary of a safe set. So it seems very different, no? The way to understand how deeply connected they are requires going to the case of exponential decay. Okay, this was the case of asymptotic normal stability. This v dot was less than 0. No? So we don't have really a decay rate for how fast we go to 0. No? So let me briefly tour you to what happens in the exponential case. And in that case, you will see the connection, how they are dual one to each other. So let's consider, yes.
I would understand the importance of stability and stabilizing using control. What is the importance of invariance and enforcing invariance?
You don't, the class, so control barrier function were introduced in 2014 in the context of cooperative adaptive cruise control. So you want to do your own stuff, but you don't want to crash into that car. I want to do my main task with the manipulator, but please, I don't want to crash into that obstacle. So I didn't use the word, but this is normally referred to safety. To safety, no? Then that set C is called C because it's not because, it's the safe set, no? It should be S, no? So I called it C. But I mean, it's referred to the safe set. The idea is that the stabilizability is kind of the task, as you said, no? Instead, the invariance is the safety. I want to be safe. In fact, this is becoming very popular in RL and learning schemes. I'm doing some work with that because learning schemes don't have a safety guarantee, no? So you can filter, say, a policy learned with RL, with the CBF, and then you are also safe, no? That's the idea. They like it a lot. I mean, there are, I'm sure that Stefano and also myself, we have some, we don't agree that this is really safety, because this concept of safety is a concept which purely depends on the state space. No, here you can only define safety as a region of the state space. So if you do obstacle avoidance, okay, that makes sense because you have to avoid some positions for a robot, no? Even if you have problems of relative degree, let's not go there. But say if you want to define safety as limiting the energy transfer with an external interaction, you cannot do it this way. That's why I don't like to call it safety, and I just simply refer to it as invariance, which is what it is.
But I mean, for non-interactive system is a way to describe where you want to be and where you don't want to be
Exactly. In the state
in the
space.
state space, basically.
Enforcing constraints.
No, not constraints. Enforcing a space, because a constraint is something you don't move around. I mean, it's a bounded constraint in that sense, yeah.
Yeah, but yeah, maybe this is very general. It can also apply for electrical circuit. It's not only for it's really invariant. I have a system, dynamical system with the state space, which might be n-dimensional for some reason, and I say encode my safety in building such a barrier function, such that the super level set of this barrier function is where I want to stay if I'm there. Okay. And that's it. That's and this
Like
thing.
virtual picture, I mean, robotics in medical robotics is used all the time. Robotics, not to move around certain spaces. Basically, yeah.
But then I'm also telling you that this is very cool to me, because in some sense, Lyapunov functions are very restrictive. No, Lyapunov function, I mean, it's good for doing regulation after all. Then okay, you can do it on a trajectory. I mean, but Lyapunov, all the level sets are invariant. You pervasively inject damping in our term. No, you go there. Instead, here you're really giving freedom to the system to do whatever he wants, and in the moment in which he is in a safe set. So I think it's a very useful tool.
Bumper car take-on.
Exactly.
So from so I want to ask you, because I don't know if there is a property of a function that would satisfy the thing that I want to ask. So we know that the gradient of the h is non-zero, and at the boundary it would move away from that, it would go back in, right?
Yes.
But is there a property of h such that h dot doesn't bounce on the boundary? So I guess something like h dot has to be bigger than a certain amount or something such that you don't keep bumping on the edge.
Yes, I'm coming there. I'm coming there. This is the very basic definition of control barrier function with using Nagumo. Using Nagumo's invariant. Nagumo is I really give the condition only at the boundary, which is very you can imagine that at the control level it's untractable, no? Because it means that you do a bang control at the boundary. Basically, you do nothing until it reaches the boundary, and then you push I mean, you can imagine that this is not excellent to implement at the control level. We need a smoother version of this, which turns out to be dual to the exponential version of the Lyapunov stability. And this is what I wanted to say. This is the cool part. The cool part is this one. So what we did now is Lyapunov was v dot less than 0 for each x, say, different than 0. And instead, the barrier case was h dot greater than 0 for each x at the boundary of the safe set. Okay, so this seems quite unrelated properties. It turns out that these are very nicely related in the moment in which in the moment in which we substitute this asymptotic / Nagumo condition with exponential, versus exponential version of this CBF condition. I don't know how to call it. Okay, so you know, what does it mean that V dot is less than 0 if you think about it? It means that you can project all the state in a one-dimensional coordinate, basically, and you look only at the V stores the coordinate of the state. So if the V goes to 0, you know, the state goes to 0, and you know something of the state without solving the system. You know that if we don't have only V dot less than 0, but we have V dot less than minus gamma V, we have also an exponential decay. Why? Because then, of course, this is the curve V dot equal. This is the curve of the evolution of V versus time. Okay, in case we have a linear differential equation V dot equal to minus gamma V. In this case, we have a first order differential equation, and we know that the time evolution of this V, okay, is such that it is this blue line. So to have V dot less or equal than minus gamma V, it means that the real system evolves below this curve, where this blue star is, no? So we are bounded from below by an exponential evolution. We converge fast, which is normally what it's desirable at control level, because at the control level, we don't want to converge to the origin in 2 years. We want an exponential rate of convergence. Okay, but what's going on here? This is more difficult to understand, no? But I mean, notice that we are kind of unifying the two conditions, no? So if I substitute this fake exponential condition, this exponential condition in the CBF case, I say, okay, the time evolution of H, say, is this red curve. But then, instead of being greater than 0 at the boundary, now I'm saying it's greater than the exponential version of the decay always, not only at the boundary. I say, what has that to do with the CBFs? Okay, I'm trying to convince you why. Now, let's go to the board. So I want to convince you that this exponent, in the same way as this exponential version is, say, the stronger version of the asymptotic one, this is easy to understand, no? Because if gamma is equal to 0, then we end up in the V dot less than 0. And that's exactly what happens. But now I want to convince you that having this, which is Nagumo, okay, having this condition only at the boundary, okay, we can arrive to this condition as a limit case of having H dot greater than minus gamma H for each X in C, and not only at the boundary of C, which is a little bit more tricky to see, but I hope I will convince you in a second. In particular, I want to convince you that if gamma is infinite, we go to Nagumo. Here, if gamma is 0, we return to the asymptotic case. Here is gamma, if gamma is infinite, we return to Nagumo. Let's make the 1D dimensional case, and it will be clear. Imagine to have a 1D system, okay? And I design this barrier function H, okay? Which means that I design the barrier function such that this compact interval here is the safe set, okay? This is clearly the super level set encoded by this barrier function. Here I'm saying, okay, H dot is greater or equal than minus gamma H. You understand that minus gamma H is this kind of function. I flip it and I scale it, okay? So you understand, and the bigger the gamma is, okay, the steeper I am here at the boundary of the safe set. Okay, if the gamma is very little, then I have something like this. The gamma is very, very steep, goes to infinite. Here I'm very, very steep. Okay, so I give you the intuition. Of course, there is the theory, the theorem. You can look at the proof. I give you the intuition. You can imagine that if you go slightly inside the interior of the safe set, if the gamma is very, very high, then this is very, very low. It's almost minus infinite. And then the condition says it suffices that something is greater than minus infinite. That's easy. So basically, this condition is always satisfied. But when you go to the boundary, in which by construction at the boundary, the H is 0, there you have to respect that H dot is greater than 0, but only at the boundary. Understand the game? That's why. That's why this condition here arrives to the Nagumo for gamma going to infinite in the same way as this condition here arrives to the asymptotic case for gamma equals 0. So, last bit, what does this gamma represent in the asymptotic case? In the stability case, the decay rate of the towards the equilibrium. That's easy. What does the gamma represent in the CBF approach? Yes. More
Distance once you hit the border.
more precisely, it represents where you are confident. It represents basically the higher the gamma, say gamma is infinite, then the control acts only at the boundary, pushes you at the boundary. You go back to Nagumo's case, but you ask a lot to the actuators, for example. No? Instead, if the gamma is low, you start to impose a condition on the CBF before actually going to the boundary of the safe set. You start to push the system back before. That's what the gamma represents. It's the influence of the barrier function, exactly. I mean, the barrier function, you design it to encode the safe set. And if you apply it in Nagumo's way, okay, say, then the controller really does something only at the boundary, pushes you back hard at the boundary. Instead, if you do it this corresponding to the exponential way, but for CBF, you can play with this lambda, which of course then in the general case, we are talking about class K function. I'm making it easy here. You can play with this gamma to modulate, okay, when the controller pushes you back, even if you didn't reach yet the boundary. That's the idea.
Basically the same as they do in optimization. If you want to go from hard to soft constraint.
Yes, with the difference that you will see in a moment, this algorithm, this condition will be always implemented as an hard constraint. But what makes the difference between hard and soft in this case is the choice of the value lambda. Okay, but you implement this at the level of hard constraint because you want anyhow safety.
Because I mean the boundary is still a hard constraint.
Yes, yes. For each gamma, this is stronger. In the same way as for any gamma here, I'm stronger than the pure asymptotic stability case. For any gamma there, I'm stronger than the pure Nagumo case. So the only thing is the other way around. No, here is from 0. Here is the gamma equals 0 case, is the asymptotic case. There, the gamma equal infinity case. But for any value in between, these are duals. You see, it's the very same condition. Here I have a less or equal. Here I have a greater or equal. Here I have a Lyapunov function, and there I have a barrier function. It's kind of non-trivial, but it becomes very, very dual. Very, I mean, to me it was a little bit surprising, this duality which exists, which after all is not so surprising. By the way, you know this notation. This is just the Lie derivative notation. This is just another way to write V dot and H dot. Don't worry about it. Okay, it's the dependence on the control of the V dot. Why isn't that surprising? forget a moment about the Lyapunov thing. That I think this is a aha moment for me. If you take the H, the barrier function, and you produce another function which is minus H, you produce the flipped version, call it V. Then, of course, we have a function which is V dot, and then the inequality sign reverses. And then we have a Lyapunov function. In fact, for every barrier function like this induces a Lyapunov function, which it is like this, basically, which stabilizes the set, which is one of the properties of the CBFs. Okay, this is a detail. I think this is a cool detail, but if we can go there later if you want. I want to finish here. Questions?
Possible to find this H function?
So in the same way as it is tricky to find the Lyapunov function for understanding stability of system, of course, you need to be very creative and not creative, because after all, you design the H in order to encode invariance of a set that you know. So it's not difficult to write down the CBF.
Because you're trying to constrain the state space somehow.
Yes, but once you know what part of the state space you want to constrain, that it's kind of easy. But the problem are different. The problem is that you have also this condition for the CBF to be such that it is in general difficult to solve the optimization.
But you can always generate this by summing a bunch of functions which have a bubble, right? I mean, you say that's the region I want to do it. You put a lot of bubbles, so you sum them, and you have something that is positive, right? What I call, I mean, not a Gaussian, but a function which has
It's like I define a potential field.
yeah, it's like a Gaussian. You could use a Gaussian, right?
There is a paper that the CBFs generalizes potential field method. For every potential field, there is a corresponding CBF. Yeah. So what I want to say, the last thing that is important to understand is how this thing is used in practice. No? Because, I mean, we were talking about existence of controllers such that this holds. Okay, but how do you do it? No? In continuous time, this is the solution. In continuous time, we solve a quadratic program like this, which is very, it turns out to be very efficient for this class of control affine system to be solved also at 1000 hertz or stuff, or it's very fast to be solved. Why? So here I said the idea is to use a scheme in which we have a nominal controller, as AM says. Well, why should we use the CBF? I understand the stability. Well, why? Say you have a nominal controller for your main task, which does stuff. No? The idea is using the CBF as safety constraint. In the best possible case, the CBF algorithm does nothing because you are in your safe set. Okay, in that perspective, you basically solve this problem. Okay, solve this problem in which you want to minimally modify a desired control action. Okay. To solve at every time step, the optimization problem, which just says, okay, I want my CBF constraint and possibly CLF constraint to be satisfied. And what happens is something like that. Basically, I have a desired control action, and this optimization transforms my desired feedback control into a new feedback control. Okay. Such that it keeps invariance and stability of the equilibrium. And this is how it is used. And the great success of CBFs in the last 9 years, I would say, is because this optimization is very efficient, works well on board, is very fast, and has been implemented in many different ways. Here I'm giving the the baseline version, but I mean, there is a lot of technicalities, there is problem of relative degrees, but this is the concept. There's not much more in terms of implementation, in terms of theory. This is what's going on. And you can play around with the parameters, and you can relax the optimization and add slack variables to improve the feasibility and this kind of stuff. But the idea is that if you're able to solve such an optimization, and the fact that this optimization is feasible is not obvious. Okay, that's the thing. No, technically, for this H to be a Lyapunov function, this optimization must be feasible, which is not always the case. So there is a lot of technique to make the problem feasible, adding slack variables but this is the idea. No, if you're able to do it technically, then you have a system who does your stuff, which also avoids some unsafe region, and it works. This is what I wanted to say about, in general, about Lyapunov theory, barrier function theory. I hope I gave you the main intuition of what this does, what it can do. I hoped to take less time, but I mean it's a good idea to, I think, to respond to some questions if there are some. The next part of my presentation was about to present to you what I did with this in my latest results, which I submitted to LCSS and CDC. I received the reviews the other day, were very good reviews. So I mean, I'm also happy about how the process is going there. So if you want, we can go on. I can tell you briefly what I did with this, what my contribution was lately. Otherwise, if we want to keep it at a more conceptual level and respond to Q&A, I'm good also with that, as you want. Exactly, that's the problem of the relative degree. That's I would say that's the main problem. No, that is when we are in the mechanical domain and we have a torque controlled system, not a velocity controlled system, but a torque controlled system, then the relative degree of the system is 2. That is basically the U does not enter the H dot. Okay. So there are at least 3 different approaches to overcome the problem, like backstepping, say to change of coordinates, to build the control barrier function in different spaces and so on, or to design, say, Lyapunov, to design barrier function, which they call energy-based barrier function, which turned out that I kind of generalized them in my contribution, which is tricks to add pieces in the control barrier function, in the barrier function, to add pieces, to add a piece of kinetic energy. Say, so if you basically want to do only obstacle avoidance for a mechanical system, so that it turns out that the CBF is built to be function only on the positional state of the system, because you want to do obstacle avoidance. So in the moment in which you calculate the H dot, exactly as Antonio said, the LGH is 0. The U does not enter the H dot, so not feasible. You cannot do it. It turns out that if you design the CBF, say that this is the CBF for doing the CBF. This is, say, the CBF for doing obstacle avoidance, which depends only on the Q variable. No? If you choose a CBF, which is minus the kinetic energy of the system plus a constant times the CBF that you want to use for doing obstacle avoidance, for a sufficiently high constant alpha E, the safe set of this guy tends to the safe set of that guy. So you can use this kind of tricks to overcome the problem of the relative degree. But this is another solution. There are multiple solutions. It's nice because this CBF business is very much connected to Lyapunov in this dual sense, which I discussed. So in some sense, it's very much connected to energetic arguments that I'm used to use. in this setting. And this was exactly my contribution. My contribution was, okay, I go briefly through it. It's a figure, say, borrowed by Rami's thesis. The idea is, so say we want to do energy-aware control or passivity-based control or this kind classes of control schemes. Remember that this is the framework in which we use CBFs. We have a desired controller, and then we have a safety critical filtering. Why do I call it safety critical filtering? Because basically, in the moment in which I am well inside the safe set, this U safe is 0, no? This condition is satisfied, and the solution of this controller is just the U desire. Then, I mean, this doesn't make any job. This is the part which is modulated by the CBF. So imagine that this desired controller comes from a passive design, comes from a design in which the controller is a set of dampers and springs and whatever, and drags you the robot around, and you have energy tanks, and you have virtual springs, and so you have these passive controllers. My question was, okay, this is a very nice framework, and in my opinion, the problem of this framework is that there is a lack of constructive way to actually design the logic of this virtual, say, physical elements to do tasks. Okay, you need to be very creative, no, in saying, okay, I have a damper. How do I implement the damper? If I want to do variable impedance, how do I vary the damping? That is the problem also of variable impedance. No, how do I vary the impedance parameters on the basis of the task? It's not an easy question, no. So my question was, and this is indeed what I what I answered in my contribution, which is on the archive, by the way. It's that one. So if, say, the desired control system gives rise to a passive closed loop system, which roughly speaking means that, okay, I can interpret it as a controller which acts in an energetically bounded way, for example, by means of dampers and springs and so on. Under what conditions does a safety critical filtering maintain the passivity of the system with the same storage function? That is basic, roughly speaking, under which conditions does the system still behave that, okay, of course, in general, it doesn't. No, I can put funny CBFs that brings me in some strange reason of the state space and inject energy in the system. Roughly speaking, the question here is, what are the CBFs that I'm allowed to use such that the system does not inject non-passive energy flows in the system, such that the control system is still passive? It turns out that the CBFs that I'm allowed to use are a generalization of the CBFs which are used for this funny trick of solving the relative decay problem. And okay, in general, they encode the logic of, for example, these virtual dampers. I made the simulations, I made the experiments, for example, for a cart pole, very simple, in which I say, okay, my nominal controller is a spring. And the system has no dissipation. It's no dissipation. So what does the system do in the nominal case? Just oscillating around in a nonlinear way, because then there is this other part and so on. Say, okay, I use a CBF which enters this class of CBF which maintain passivity, which I give, by the way, necessary and sufficient condition for this to exist. So it's really equivalent, no? Say I want the kinetic energy to be less than constant, say for safety reasons. Okay, then I choose this CBF, of course. This encodes the safe set that the kinetic energy is less than a constant. And I let the system evolve with more energy than the allowed one. Okay, some stored in the control spring and some in the initial kinetic energy. And basically, you see that what happens is exactly what expected. The system is passive, that is the total energy of the control system only decreases. No? And the moment in which it decreases is the moment in which the safety critical filtering is active, and which is the moment in which the control barrier function goes almost to zero. That is, we are at the boundary of the safe set with some degree of modulation given by the gamma. No? And basically what it does is this funny damper, no, which is encoded by the CBF, turns on and off only when desired, basically, encoded by the CBF. So you have really these dampers that if you would implement this with if statements and so on, it would be tricky. Eh? You would require a lot of fantasy, you know. Then you would say, okay, if I am in this, then dump this, and instead this does it automatically. That's the cool part. It does it automatically, it does it alone. You just need to design the CBF, and I give you condition, you are allowed to choose this one, and the system remains passive. And then automatically the system dumps the energy in the moment in which it desires. So I did it for different E-bars, for different kinetic energy, and you see that I really control the steady state oscillation around the set point just by means of the CBF algorithm. The damper works in a region which is encoded by the CBF. I did the same for another CBF, which is the kinematic constraint. That is, I'm giving the same control input, okay, which would oscillate around 1 forever. But then I say, okay, this requires some theory to understand the safe set. But the point is that for a sufficiently large alpha, the safe set of the CBF is basically Q less than Q bar. So for different Q bars, you see, and this is again one of the allowed CBFs which maintain passivity. And you see that for different Q bars, I still have passivity. That is, the system still only dissipates energy. But you see the safety critical filtering activates in a way.
Dissipating.
Exactly.
But you could also do it elastically. As long as you have a boundary, the only thing is the boundary can be, as long as the boundary is passive when it's active, it could be a spring that brings you back inside.
Yes, you can. Yes,
I mean, as long as the only thing is it should be passive and activation to be close to the boundary, so to speak.
Yes, but again, exactly, of course, it can be done. But again, I think the power of this approach is the fact that you don't have to design it constructively. I mean, this is just, you see, for different, say, I think what's pretty illuminating is the case Q bar equal to 1. No? Here I have a nominal controller, which would push the system to Q1 and then oscillate forever around Q1. Instead, I add to this logic a CBF which says, please be less than Q1. And you see that the spring and this variable damper, which is at all effect a variable damper, and the fact that this is a variable damper is proven in the theorem, is proven in the paper, because I proved that the system remains passive, which means basically that this acts as a damper in this circumstance, which is not an obvious thing, no? Because this the control effect from this comes from an optimization. It's not an obvious thing, but the spring and the CBF effect interact in such a way that achieve regulation basically to 1, even if there is no dissipation term, there is no de-action.
It could be, what I'm saying is, for example, locomotion, you may want, and of course you can define it by the proper definition, but you don't want this to dissipate. You may want something that, you know, keeps the energy but bounces within a certain region.
Yeah.
Okay, in that case, you would rather have a kind of elastic compensation, non-linear compensation, rather than a damping.
Yeah, I agree, and I don't know if in that case the control barrier function setting would be preferable. I think then it would be better to use, say, all the elastic elements.
I think you would have a situation would be with a control barrier function with that kind of dynamic extension that you basically would put the spring state inside it, and you should be able to do it exactly the same way.
Yeah, I agree. Yeah, last comment. Notice something which is, in my opinion, cool, is that with this idea that all these classes of the fact that all these classes here of CBFs keep passivity of the underlying system if the underlying system is passive, means that you can integrate any control schemes which is implemented in a passive way. And you can do obstacle avoidance, for example, on it without compromising stability of the system, which is a big deal in control theory, without compromising stability of the system, only by implementing this quadratic program of the CBF. So the only thing you need to worry about is how to define the CBF. The system does it alone, and there is a solid theory which says, okay, you know what, the system remains passive, which means that it remains stable.